So I will go ahead and kick things off. We do have a guest speaker today, which is really exciting. We have G. I believe that's how I pronounce it. If it's wrong, please let me know. Um, is that right?
Yes.
Okay, awesome. Hi, G. So G is a PhD candidate right now, and he's working on a couple various aspects of large language models, including factuality, reasoning, and safety. And so we're excited to hear a bit about his research today, which his research aims to develop powerful and reasonable large language models and apply them to solve real-world problems. So I'm really excited for this session. G, do you have slides that you'd like to share screen?
Yes.
Okay, perfect. Go ahead and do that.
Okay. Yeah. Thanks for the invitation. Let me share the full screen. So my name is Huang. I'm very happy to share our recent work. Large language models cannot self-correct reasoning yet. And this is joint work with Xingyun, Swarup, Stephen, Adams, Xingyun, and Danny. And this work will appear at iClear 2024. So as we know, that large language models like ChatGPT are very powerful. They can solve many questions, including those requiring reasoning. For example, however, language models still make many errors in their reasoning. For example, so this question is, Christina is planning a birthday party and needs 0.75 gift bags per invited guest because a quarter of attendees don't show up. She invited 60 friends. Gift bags are $2 each. How much will she spend? And the ChatGPT can generate a response containing step-by-step reasoning. However, ChatGPT make an error in its reasoning. So the error is the model misunderstand that so the model the attendance is just 9. This is because that in fact here the one quarter of attendees don't show up is the reason that she needs 0.75 give back. However, the model multiplied expected attendance by 0.75 twice. So this make the final error, final answer 18. This is long. And how can we mitigate this? So there is a proposed concept named self-correction. So which aims to create the answer based on the model self. But before doing that, let's connect to the humans first. As we know, humans may also make mistakes in their initial attempt to answer a question. However, after reviewing the answer, they may find the mistake and correct it. And so in fact, humans learn from collecting errors. What does this mean for concatenate self-correct reasoning? This means that it can self-improve capabilities. And if a human and also a model can iteratively self-correct, improve their capabilities, what does this mean? This means, this in fact a promising direction to AGI. So how to enable models to do self-correction? We can try to prompt large language models in 3 steps. In the first step, we can prompt the model to perform an initial generation. This is just similar to standard prompting. We will give the model a query, and the model will generate a response. And this response may contain some errors. And in step 2, we will prompt the model to review its previous generation and produce a feedback. And in this step, the model will possibly find that it makes some errors in its initial generation, and they will generate such the rationale in the response as a feedback. And in step 3, we will prompt the model to answer the original question again with the feedback. And ideally, the model is expected to correct some errors in its initial duration based on the feedback. And so in this case, so it will change the initial incorrect answer 18 to a correct answer 24. So what about the ability of language models to self-correct their reasoning? According to existing literature, it seems that large language models possess a strong ability to self-correct reasoning. For example, on GSM-AK, it's observed that the language models can achieve a 70% performance improvement post self-correction. And on common sense QA, there is observed a 50% performance improvement post-server correction. However, I feel that the improvement is a bit counterintuitive. So we try to replicate their experiment first. And here, so we follow previous work to use the correct level to determine when to stop the self-correction loop. This means that so we will prompt the model to perform some maybe initial duration, and then we will use ground truth labels to check whether this answer is correct or not. If the answer is already correct, we will stop the self-correction loop and use this the generated answer as the final answer. If it's wrong, we will just like as described previously, we will prompt model in 3 steps. So by providing it with a feedback prompt and to generate a feedback, and then prompt again to generate the final answer based on the feedback. And with this setting, yeah, we do find that the models can achieve significant performance improvement post-server correction on all the 3 benchmarks. This aligns with the result in previous papers. However, some of you may already find the issue here. So is that in a realistic setting, so we don't have the ground truth level. So how can we use the ground truth level to judge when to stop the self-correction loop? And if we already know the ground truth level, why we still need to let the models to solve this math problem? So if we remove the usage of labels, it's not very surprising that, in fact, the model cannot perform as well. And in fact, on all the benchmarks, we found that if we remove the usage of labels, the performance of the models even drops after self-correction. And on some dataset like common sense QA, GPT 3.5 even achieve a significant performance decrease post self-correction. So is this because that is the prompt we use is suboptimal? So we also try to test on different feedback prompts. For example, assume that this answer could be either correct or incorrect. Review the answer carefully and report any serious problem you find. However, with all these other feedback from prompts, we also found that the model cannot achieve better performance. And this result is tested on GPT-4 Turbo, which is the latest kernel of ChatGPT. We also test on open source model, such as Llama 2, and we found that the issue is more severe. So on both GSM-AK and the common sense QA, the performance of Llama 2 post-server correction dropped significantly. For example, on GSM-AK, with standard prompting, the initial accuracy is 62%. However, after 2 rounds of self-correction with this feedback prompt, so we observed that the model can only achieve 36.5% accuracy. So this supports that, in fact, the models struggle to self-correct reasoning without the usage of labels. And what's the reason? Here we present a very simple empirical analysis. So we try to categorize the answer changes post self-correction. For example, for GPT 3.5 on GSM-AK, there is 75% of cases that the model does not change the answer. And in some cases, the model will change a correct answer into an incorrect one. And in other cases, the model will change an incorrect answer to a correct one. And also, it's also possible that the model will change an incorrect answer to another incorrect answer. However, here, one key is that we found that the model there's a higher chance that the model changes an correct answer into an incorrect one instead of changing an incorrect answer to a correct one. So this causes the performance decrease. And here is one example. So the model initially generates answer this question correctly. However, after we instruct it to review its previous answer, and improve the answer based on the feedback. We find that the model will change the initial correct answer to an incorrect one. And the underlying reason is that language models struggle to verify their reasoning. While previous work assumes there is a presence of a perfect external verifier, however, as we discussed before, this is not a realistic setting because if we already so in fact, in many real-world settings, there is not such a perfect external verifier. And if we already know the answer, so like previously work, they use one truth level to check the correctness of the answer. But if we already know the answer for the math problem, why we need to prompt the models to solve this math problem? Cool. Okay, so by examining the literature, we find there is another form of a self-correction, which is named multi-agent debate. The method is also very simple. So we will treat different copy of large models as a different agent. And initially, the model will we will prompt the model to generate different response by setting a high temperature, and each response will serve as the response of each agent. For example, here there are two agents. And in the second round, we will try to prompt the model to examine the response of other agents and update each agent previous response. And in this way, the model will likely to improve their response based on debating with other agents. So what about its performance? Yeah, first, it's true that multi-agent debate can significantly improve the performance by comparing with standard prompting. So, for example, after 2 rounds of multi-agent debate, there is about 5% performance, 6% performance improvement. However, if we compare multi-agent debate with self-consistency with an equivalent number of response, so in this case, both the multi-agent and the self-consistency generates a 9 response. We found that, in fact, multi-agent debate does not outperform self-consistency. And even the performance is much worse than self-consistency. So by examining some generation output of multi-agent debate, I also find that, in fact, the model does not really debate each agent. The agent does not really debate each other. So in fact, this is more like a means to achieve consistency across multiple generations. So the implication here is that large models do not self-correct reasoning through debate. Okay, so based on our study, we found that large models struggle to self-correct reasoning. However, in the existing literature, so for tasks other than reasoning, we do find that models can achieve a significant performance improvement post self-correction. For example, in self-refined paper, so it observed a very significant performance improvement on tasks like cinema reversal and constraint generation. And also in another paper, named CI, done by Anthropic, we also found that with self-correction, large models can reduce the harm of a response after maybe 7 rounds of self-correction. So here it's important to understand when self-correction can work, when self-correction cannot work. But before discussing this problem, I'd like to point out one thing is that in fact we also need to care about the quality of the initial prompt. So for example, on the constrained text generation task in the self-refined paper, so we found that also the task is constrained text generation, so it's defined as given a list of concepts generating a sentence containing all the concepts. And we found that this requirement, the requirement that the output sentence need to contain all the input concept is not clearly specified in the initial prompt of self-refined paper. So their problem is formed in this way, like they will give the model 8 in-context examples, which each example, the input is a concept, and the output is a list of concepts, and the output is sentence containing all the concepts. And then followed by a target input sequence, which is the input concept, list of input concepts. However, in the layer feedback prompt for self-correction, so they will instruct the model to identify the missing concept in the output sentence, and instruct them to include the missing concept in the updated generation. So it's not surprisingly that because in their feedback prompt they have more clearly instruction. So it's not surprising that with self-correction, the model can achieve better performance. However, if so, why not we just simply instruct the model to include all the concept in the initial prompt? Like we can simply write the prompt in this given list of concepts and followed by an instruction by the reasonable paragraph that includes all of the above concepts. And we found that in fact the model can already achieve very good performance with this prompt. And this outperform the performance post self-correction of the self-refined paper. And also, if we apply their feedback prompt to try to do self-correction for the response generated by our prompt, we found that the result is similar to our previous result, is that the self-correction will cause performance decrease. So yeah, let's return back to the question: is when does self-correction work? To answer this question, we can look at the format of self-correction and standard prompting. So for standard prompting, it can consider as named as something like a pre-hoc prompting. So we will give the model a prompt and generate a response. And for self-correction, it can form as a post-hoc prompting. So here, the prompt will contain several components. One is the initial prompt and the initial response, and also a feedback prompt or something else. And then the model will be conditioned on this prompt to generate a response. So, but here, so in fact, this prompt is also not special. It's also like just an input sequence. So when self-correction can work, it will because that the feedback prompt, if the feedback prompt can, the prompt one here can contains maybe more instruction, more clear instruction, and also maybe some external feedback, the model can achieve better response. Otherwise, it's no different to the initial prompt. So here, so the conclusion is that a scenario in which self-correction enhanced model response occur when it can provide a variable instruction or feedback that is missed by pre-hoc prompting. And for safety, self-correction can serve as a means to reduce the harm response through a post-hoc examination with more principles. This is just about changing the style of a response. It's easier for the model to achieve. And why this approach is still useful is because that it's difficult for us to include all the principles in the initial prompt. So we would like to include maybe the principle in the feedback prompt. This can make the response safer iteratively. However, for reasoning, review your previous answer and find problem with your answer does not necessarily provide any benefit for reasoning. This is because for reasoning, it usually requires the enhanced capability of a model to solve a more difficult task. So no matter how we instruct the model to review its previous answer and find proper answer, if it cannot solve problem, so no matter how it reviews his answer, so it still cannot solve. So, and now I like to have some discussion. So first, it should be noted that we are not arguing that self-correction is useless. So as we see that self-correction may still be beneficial for aligning response with certain preference. For example, making a response safer. And the second part is that our result indicates the models struggle to self-correct reasoning intrinsically. So we can try to leverage some external feedback, but if we can leverage some external feedback for correction, the story will change. For example, we can leverage some external feedback from tool, from environment, or from humans. And in this way, intuitively, that the model can, if the feedback is of high quality, intuitively, that the model can achieve better performance based on the feedback. The third point is that from our result and also some existing study, so we do find that self-consistency can achieve much better performance. So we can try to employ self-consistency as a method of self-verification. And this is also have already been used in some existing methods such as tree of thought. So last, I like to provide some guidelines for comparison. First, when doing the comparison, we need to consider the inference cost of this method. So usually, the method like self-correction needs a multiple model costs. This will significantly increase the inference cost. And it may also generate multiple response. So it's recommended to compare the performance of self-correction with self-consistency with equal number of response. The second point is that we need to concern both the quality of the initial prompt and the feedback prompt. So it's somewhat meaningless that if we just design a very bad initial prompt and try to let model to generate a better initial response, and then we use a very careful crafted feedback prompt, which may possibly include more instructions, more clear instructions, so the model can generate better response post-spec question. But this is not very meaningful because we can also try to design a better initial prompt and get a good initial generation. The third point is that so when we try to leverage some external feedback for self-correction, we need to judge whether the external feedback is reasonable. So, for example, like some of the principles, they use ground truth levels as the external feedback to judge whether the judge whether the answer is correct or not. This is meaningless. Just because if we already know the ground truth levels, it's no reason for us to do self-correction to prompt the model to solve this problem. But the result here can only be served as an oracle. So which means that when an external perfect external verifier is available, so how the model will perform. Okay, here is a list of takeaway. The first point is that large language models struggle to self-correct reasoning intrinsically, as shown by our results. And here, the underlying reason is that large language models struggle to verify their reasoning. Second, so since the models struggle to self-correct reasoning without external feedback, so external feedback is essential for large language models to enhance their reasoning. And here, this can be connected to the self-improvement of large models. If we can try to instruct models to leverage the external feedback from environment, from tools, so possibly the model can try to self-improve its capabilities. And if we can done this iteratively, and model can self-improve themselves iteratively, and with maybe very enough computation resource and also a long training time, so possibly this could be leads to something like AGI. But before expect this, we also need to maybe think about a more fundamental question: are large language models really able to reason? So in fact, this is a topic that I was invited to discuss for this talk, but I feel that this question is too difficult to answer, and also it's too broad. So I changed to mainly discuss our recent work. But here I like to, since we have time, I'm happy to share some of my opinion about this question. So before answering this question, we need to first know what's reasoning. So 1 year ago, I asked ChatGPT this question. So ChatGPT give a very good definition. Is that reasoning refers to the process of thinking through a problem or situation in order to form a logical conclusion or make a decision. It involves using evidence, facts, and logic to arrive at a solution or answer. Reasoning can be deductive, abductive, and can be performed using informal method. So the definition here is not very formal, and usually in the existing literature we cannot find a formal definition. And in fact, for many papers or reasoning in large language models, they does not give a definition for reasoning. But one thing here is that it's about to reason about new knowledge, based on the existing knowledge. And this is not reason is not just simply refers to something to recall and memorize knowledge from maybe the model's parameters. It's need to inference something new. So let's return back to this question. Are large models really able to reason? So I like to share some observations in existing literature. The first is, so in fact there is, so in the literature, in fact there are different opinions about this question. So for example, for the study by Kojima, their title is large models are just short reasoners. But for another study, so its title is GPT-4 can reason. So and here I like to elaborate a bit more based on existing literature. So first, there are some evidence that the models are likely to have a certain level capability to perform reasoning. So for example, they can reason step by step with chain of thought prompting. And they also achieve high performance on various tasks requiring reasoning. For example, they can surpass the average human rated performance on 70 of the 23 tasks in Big Bench hard, which many of them are tasks that requires reasoning. And they also have some reflection of human-like content effort on reasoning. This means that although the models they may make some errors, but as we know that humans also make errors, and they find that the patterns and the error patterns of humans and models share some common patterns. So for example, both large models and humans are biased by the reversibility of the conclusion when reasoning. And however, there is also some observation that suggests that models may not make their predictions based on reasoning. For example, the first one is very simple. So the models make mistakes in their reasoning. And the second part is that the models struggle with tasks that requires complex reasoning. For example, in these studies, they have shown that for some tasks that is very easy for humans to do, maybe achieve a perfect performance. But for learned models, they may just make something like make random guessing for these tasks. The third point is that the performance of large models on downstream tasks has been found to be sensitive to the frequency of certain terms. If learned models, for example, for solving math problems, if learned models have seen a number more frequently in its training data, it can achieve better performance for this problem. But So here, so if learned models they make their prediction based on reasoning, so the performance should not be sensitive to the frequency. And the first part is just like what I have discussed, is that large models cannot self-verify or self-correct their reasoning. Last, in a study done by me in 2022, we also found that the models struggle to associate relevant information that they have memorized. I'd like to elaborate this a bit more. So, as we know that humans can easily associate closely related information that they have memorized. For example, given this sequence, so by reading this sequence, or if we have memorized this sequence, so we can easily judge the email address of this person, Zhengdu, is abc@xyz.com. So what about the ability of lay models to do this? So in fact, this is just a very basic understanding and tasks. So can lay models associate this kind of information they have memorized? And it also should be noted that in this context, that in fact, we actually hope the models not possess this ability, because this will possibly cause some, if the models can answer this question, it possibly could cause some issues of privacy leakage. And to test this, so we design experiments in two settings. In the first setting, it was named verbatim recovery. We will use the tokens preceding the target email address in the training corpus as the input of the model to elicit the target email address. For example, this sequence, have a great day, Zhengdu, abc@xyz.com. So this is a training, is a sentence in the training data of, in the pre-training data of the testing language model. And we would like to see if we use the prefix of the sequence, which is have a nice day, Zhengdu, whether we can prompt the model to generate the suffix of the sequence, which is the email address. So this testing aims to test the memorization ability of the model, and it's just merely based on the next token prediction ability. And the second setting is association tag. So we will try to prompt the model with different templates. For example, the email address of somebody is. Then the name of the person and the email to see whether the model can recover the email address of this specific person. And also we observe there is a pattern appear in the training data of the training data of a linked model, which is original message from mail 2. And so from our experience, the first finding is that linked models do memorize a large number of email addresses correctly. So for the verbatim recovery setting, so where we give the prefix of the sequence to see where linked models can recover the suffix of the sequence, we found that linked models, 3 billion parameter linked models can predict 9% of email address correctly. However, if we just give the model a prompt like the email address of somebody else, or name some email, we found that in fact the models cannot do very meaningful predictions. For example, for this prompt, the email address of somebody else, so in fact only one email address is predicted correctly, and the accuracy is just about 0.03%. And even we give the model with some in-context examples, the model achieve a bit better performance, but the performance is still under 1%. So this means that although linked models they memorize the email address, a large number of email address, which is about 9%, in the setting, testing in the setting, but they cannot associate the names with the email address well.
Which model is this?
Sorry?
Which model is this?
So here the test model is GB-Neo.
Okay.
The family of GB-Neo, Yeah, thank you for your question. Okay, I think I can continue. And and then so here one interesting finding is that so for this zero-shot D setting, so we use we use a pattern observed in the train data, which is our original message from Neo 2. So we found that the model can do pretty something meaningfully, and it can recover about 1% of email address correctly. And so here it's also interesting to compare this result with the zero-shot C setting. In fact, zero-shot C setting is just a shorter version of zero-shot D, but it cannot predict any email address correctly. But just with a long test pattern, so the model can predict some email address meaningfully. So this means that long test patterns bring risks. And in a follow-up work, we also test on more bigger model, like 20 billion GBX model. And we find that the model do achieve higher performance with a higher number of parameters, but the performance is still not very high. For example, for the email address is about 3%, and for the phone number is about 1% accuracy. So why does this happen? This is because of verbatim recovery. This is just like given a prefix to predict a suffix. And it can be simply based on the next token prediction. This does not need any understanding and reasoning. But for association tag, so this sequence is likely not appear in the training corpus of the model. So it does require a shallow level of understanding and reasoning. So the model can associate this email address with the person, and then given this prompt, it can predict the email address. And this also aligns with the recent finding named the reversal curse. So what they have found is that the models trained on A to B cannot predict B to A. For example, So in the training data, we will provide the model with a question like who is Tom's mother? So, and the answer is Tom's mother is Mary. But in testing, if we reverse the question, so who is Mary's son? So the model, in fact, does not know that Mary's son is Tom, although he already trained on a data, including example, Tom's mother is Mary. Okay, let's return back to our question. Are large language models really able to reason? So here, my personal opinion and my suggestion is that don't treat this question as a binary yes or no. So it usually depends on the requirement and the definition. For example, if our requirement is that large models should not make any reasoning errors, but this possibly never to be achieved by any general intelligence system. So because we know that humans also make reasoning errors. Humans also, although it's observed that language models are sensitive to the frequency of terms in the trained data, but we also know that humans reason better about things with which they are more familiar. And also, humans also struggle to self-correct reasoning intrinsically without the help from others. And the second level may be something like the model should reason about a new unseen problem based on existing knowledge. And although I don't want to show any evidence here, so I believe that the models have certain ability, but this is still far from satisfactory. The third thing is maybe something like the models should reason based on learned heuristic or patterns. And the models usually have a good ability to do this, but this is still not perfect. And here, my opinion is that, so first, in fact, about the definition of reasoning. So as I said before, that there is not a clear definition about reasoning in the existing literature. And I suggest to treat reasoning as a blend of logical heuristics. And the second is that just don't try to answer such kind of question with a binary yes or no. Otherwise, it's very likely we will be overly optimistic or pessimistic about the capability of a model. We need maybe a more balanced understanding of their capabilities. So several takeaways here. First, are large language models really able to reason? So we don't try to, I don't suggest to answer this question as a binary yes or no. And the thing is that language models, they should have a certain level of ability to reason, even they may based on learned heuristics and patterns. And however, language models, their reasoning abilities still leave much to be improved. But in terms of risk, this actually limits some level of harmful usage. For example, as our study shown that although language models may memorize a piece of sensitive information, it may not easy to query this information with the user prompt. So, and last, I like to do a summary. So first, in our first work, we observed there are limits to language models' abilities. For example, large models struggle to self-correct reasoning intrinsically. And based on this finding, the implication is that external feedback is essential for large models to enhance their reasoning. The second point is that the limits of language models' ability also provide some level of protection. And in our study, we have found that language models may not easily, so in the study, it suggests that the model may not easily to leak some information they have memorized. And in fact, in our study, we test on models that without safety alignment. For model with a safety alignment like ChatGPT, I think models will also tend to refuse such kind of sensitive information. So this also can improve the level of safety. And the third point is that try to be critical and balanced. Don't be overly optimistic or overly pessimistic. Our goal is to balance different aspects, achieving high capability with minimal associated risks. That's all of my presentation. Thank you. And since we have time, I think I'm very happy to take some questions.
Thanks, G, for the presentation from the Cohere AI community. I had one question. For example, in the paper that the focus is mainly on intrinsic self-correction of the models itself, right? So what are the methods that you would suggest that can be used to improve these reasoning capabilities or self-reasoning capabilities?
Yeah, this is a great question. So let me find a slide. So for the reasoning capability, so because our study suggests that in fact it's difficult for a model, to do this intrinsically. So possibly we can try to leverage some external feedback for correction. So for example, we can leverage some feedback from the tool, like a code interpreter. So, and then we can receive the feedback from the interpreter. And it's also something like we can try to prompt the model to explore the environment and maybe to receive some natural environment feedback from the environment. And in this way, the model can leverage the feedback from the environment and to improve its response. And third point is also we can also always try to maybe leverage some high quality feedback from humans.
I believe there's a question in the chat as well.
Okay, the question is that could you share my thought on the existing method challenges of evaluating self-consistency of large language models? So, okay, I think I can use the result in this slide. So first is that it's about self-consistency. So here, by default, self-consistency is a method that using the majority voting to achieve a consistency for the model response. And later, in fact, we can also try to use the model itself to try to find the most consistent answer. This also, I think, is all work done by DeMind. And here, so like for the method like multi-agent debate, they also try to achieve a consistency through a form like debate. And in terms of the form, in fact, the self-consistency method can be implemented by different approach. But here, my suggestion for the comparison is that first we need to consider the inference cost, which is maybe can be reflected by the number of responses. We need to try to maybe compare the method with the equivalent number of response, and this could be more fair. Yeah, and the second is about the prompt design for both the baseline and also the suggested method. So we need to care about the quality of the prompt for all the methods. And this can also, in terms to achieve fair comparison. Yeah, thank you for your question. Okay, the question is, I'm curious about the potential of using knowledge graph with large models for reasoning. Is it possible to effectively use them to solve complex reasoning tasks? Okay, this is a great question. So first is that I'm thinking that, so this in fact is about the application of knowledge graph. So for knowledge graph, I believe they are still useful maybe in specialized domains. So where it's easy for us to construct maybe a high quality and relatively complete knowledge graph. And so in this way, we can try to leverage knowledge graph in a specialized domain to achieve the performance of model for these specialized tasks. But in a general setting, so in fact, it may be difficult for us to create a complete knowledge graph. Usually it's far from complete. So in this setting, so because the knowledge graph is complete, so if we ask an open question, in fact, it's difficult for us to to find maybe the reason path in the knowledge graph. So in this case, the use of knowledge graph may be a bit limited. So my personal opinion is that for knowledge graph, it may be still useful for some specialized domain when we have a high quality knowledge graph for this domain. And in this way, we can try maybe to leverage the knowledge graph reasoning to improve the reasoning performance of language models. This is also something like to provide some external feedback from the knowledge graph to help it to reasoning. But for a general domain, so maybe it's somewhat difficult to have a high quality complete knowledge graph to help the model to answer any open questions. So I think we have one more question. I understand that external tools can be connected to current GPT model to improve their reasoning capabilities without the latency associated with this approach. what other potential downside exists with this approach besides the actual imputation work? Okay, yeah, this is a great question. So what I'm thinking is still about, so if we can receive high quality feedback from external tool, it usually can help. But so here, the key may be something like how can we reliably call external tools? So for example, how can we choose the right tools? And this may connect to some research about the tool use. And the other things is that the feedback from tools may also be always high quality. For example, if we try to use search engine as an external source of external feedback, and we do retrieval based on external retrieval, and we may retrieve some errant paragraphs from the search engine. And there is also maybe many misinformation in the search engine, so it may also mislead the model to generate some maybe long outputs. So here, I think the key is that first is that what are the tool to use, and the second is that how can we judge the quality of the feedback of the tool. Thank you for your question. Okay, I think there is one more comment from the chat. Is that it's not a question, but I also think knowledge graph are a great way to give a guardrails check reasoning when working with large models, or still experimenting with the best place for them in the workflow. Yeah, I think this is a great comment, but I think the key here is still about whether the knowledge graph is high quality and complete. And we have one more question. It's about what are you working on right now? Okay, yeah, this is a good question, interesting question. So at this moment, I'm very interested about something about only self-improvement of large models. For example, how can we try to leverage the external feedback? Because our study has shown that the models struggle to self-correct their reasoning intrinsically. So I would be happy to explore to try to leverage the external feedback for the models to self-improve their performance. And then, okay, we have a new question. Is that can we use large models vast knowledge to populate knowledge graphs? This is a good question. I think there's already some existing literature that they have shown, such a kind of a potential. So, but personally, I do not work on this direction. So I would like to suggest maybe to find some existing literature to see how they do this. I do think that the models can help to complete the knowledge, make the knowledge graph more complete. But here, still is about maybe the quality of the knowledge graph. Yeah. And so to what extent it can improve the knowledge graph. And the second question is that how this knowledge graph can be used back to help the models to make their prediction. Okay, so I think we don't have new questions from the chat. Yeah, thank you all for the question, and they are all very good questions.
Thank you again, G, for this very exciting session. We obviously, I can speak for everyone here, and we really enjoyed the session. Thanks for coming in. And yeah, we hope you do all the best with your future goals and aspirations as well.
Thank you.
Thank you.
Yeah, thank you for having me.